Welcome to you all. I'm Henri and I'll be your guide in the next few minutes. When my brother and I decided to put both our expertise together, we could never imagine the wonderful journey that was awaiting us. Being able to find a framework that unifies many different matching strategies in object detection, as well as running faster on GPU and being on par or increasing the state of the art, was a great joy. But it only really takes its value when shared with our curious fellows. Without further ado, let's dive in the wonderful world of unbalanced optimal transport. Essentially, an object detection model takes an image as input and returns multiple object predictions, represented by a bounding box B and accompanied by a label C. In our example, we have 5. In our case, there are 2 ground truth objects, the motorbike B and the pilot A. We can therefore determine a cost between each prediction and each ground truth object. In our toy example here, and for simplicity, we only consider the generalized intersection over union. During training, and based on this cost matrix, the goal is to decide which predictions to assign to which ground truth object, and then push them towards it. The remaining predictions, those that are not being assigned to any ground truth object, should be pushed towards a no object class, commonly referred to as background. But still, how do we decide which predictions we push? 2 of them? 3 of them in our example? All of them? Over the years, multiple matching strategies have emerged. The first strategy is to assign each prediction to the best ground truth object. The problem, however, is that it induces a lot of redundancy. A lot of predictions learn the same ground truth object. It can be partially alleviated by introducing a threshold value. A prediction is not matched to the best ground truth object anymore, but to the best one, provided it is better than that threshold value. If not, it is pushed towards the background. This is in fact the same as considering the background as a dummy ground truth object, which has the same cost with each prediction. Furthermore, and this may be even worse, if they happen to all be close to the same ground truth object, they may leave another ground truth object behind. No prediction matching to it. And as a result, nothing will be pushed towards it and it will miss it. On the opposite side, we may also decide to match each ground truth object to the best prediction. But for an opposite solution, we have an opposite problem. As the number of prediction is in practice much higher than the number of ground truth objects, the redundancy is replaced by sparsity. A lot of predictions are pushed towards the background. Furthermore, a same prediction may be torn between 2 ground truth objects. In that case, our final model will probably miss a lot of objects. A better alternative is to consider the Hungarian matching, which searches for the optimal permutation, the one minimizing the total cost. Now, no 2 predictions can be pushed towards the same ground truth. The matchings are 1-to-1. What our work shows is that each of these strategies are limit cases of a global framework called Unbalanced Optimal Transport. This allows us to explore a full continuum of methods in between with varying properties. Furthermore, we also show how we can regularize the solution to obtain smoother matches. Let us look now how to use optimal transport, starting from the Hungarian matching as found in detail. To perform 1-to-1 matchings, we must have the same number of predictions as ground truth objects. And this can be easily done by adding multiple dummy background ground truth objects. Another way to represent the problem is to consider a matching binary matrix instead. The total cost is now represented by the element-wise multiplication of this new matching binary matrix and the cost matrix. The 1-to-1 matches are characterized by the 2 constraints. Optimal transport relaxes this problem by considering a matching matrix not limited to 0s and 1s anymore, but despite the relaxation, the solutions are equivalent. We can also simplify the problem further by merging the 3 dummy background truth objects into one, associated with a high weight, in this case 3. As this problem is equivalent to the Hungarian matching, sequential algorithms are required. But a parallelizable solution can be obtained when regularizing the objective. In addition to be able to efficiently use GPUs, the obtained solution is also smoother. This proves to be an advantage during training, helping to prevent intempestive switches when two predictions are closer to each other. We can also have a look at the following example to illustrate this. As box 1 gets further away, the Hungarian matching will suddenly switch from one match to the other, whereas the regularized solution will be much smoother. Coming back to our regularized optimal transport formulation, we can also consider making our constraints softer by replacing them with a penalization term in the objective function. The row-wise and column-wise sums now must minimize a Kullback-Leibler divergence instead. When τ1 and τ2 tend to infinity, the divergence has no choice but becoming zero, hence recovering the original balanced problem. However, if we only consider one constraint, this corresponds to finding the solution to the closest, as mentioned earlier. In this case, each prediction to the best ground truth object. And in this other case, each ground truth object to the best prediction. And when regularizing the problem, we transform it from a maximum into a softmax. And there we are, a unifying framework for object detection. But how does it perform in practice? Well, in addition to making each epoch run faster, we also observe a faster convergence on our toy dataset with the same architecture as used in data. The smoother matchings avoiding intempestive switches is the best explanation we have. And when this boost does not happen, the model remains on par with the state of the art. As you can see, Unbalanced Optimal Transport offers a unifying framework for object detection, unifying both the matching to the closest, the softmax, the Hungarian algorithm, and opening the door for a multitude of methods in between. Furthermore, the regularized problem is well suited for GPU implementation and sometimes gives a better boost. Don't hesitate to have a look at our website, where you can find an interactive tool to try it out yourself. You will also find a PyTorch package for implementing it in your own models. All the details can be found in the paper and its supplementary material. We gladly thank you for your curiosity, time, and attention. It was a pleasure to share our work with you. And my brother R and the rest of our team hope that it will help to shape a better understanding of computer vision models in general, and in fine, help us to build better models altogether. Thank you very much.